Hello, everybody. I'm Jinghui Yan from University of Illinois Urbana-Champaign. I'm serving as the chair for the technical area on computational fluid dynamics and the fluid and structure interaction. Today, it is my great pleasure to introduce today's webinar speaker, Professor Hector Gilmos. So Professor Hector Gilmos is a professor and the Morris Goldman Chair in engineering in the School of Mechanical Engineering at Purdue University. Professor Gilmos specialized in computational mechanics with particular emphasis in isogeometrical modeling and analysis, interfacial mechanics of multiphase systems, and the simulation as the interface of engineering and medicine. Professor Gilmos' research has been recognized with multiple awards, including the Juan Seymour Award from the Spanish Association of Computational Mechanics, the MIT Innovators Under 35, the Young Investigator Award from Royal Academy of Engineering of Spain, and the Gallagher Young Investigator Award from the US Association for Computational Mechanics, the Princess Girona Scientific Research Award presented by the King of Spain to the best young researchers in all fields of science, engineering, and the humanities. And he is also a fellow of US Association for Computational Mechanics. Professor Gilmos has published many papers and give many plenary and keynote presentations in many different conferences. So Professor Gilmos, it's our great pleasure to have you. The floor is yours. Thank you.
All right. Thank you very much, Jinhui, for your very generous introduction. It's a pleasure to have the chance to present some of my work here to the TTA on CFD and FSI. So I'll be showing some work that we've been doing in the area of multi-phase flows. I will present some work that it relates only to the fluid dynamics aspects of it. And then I'll show some FSI work where we do simulations that involve multiple fluids in contact with solids, where the interfacial forces of the fluid-fluid interface are the dominant physics, and those are usually called elastocapillary FSI. So I'll show some examples about that. The majority of the work here was done by two students, Tianyi Hu and Stavista Vopalan. And I'll go ahead with my presentation with this background. So before I jump into the details of the presentation, this is a slide that I use in all of my talks pretty much, where I show the type of research that we do in my group. So we are a computational group, so everything we do starts with a code. If you look carefully at this code, you'll recognize isogeometric analysis functions here, which we have been using for a long time. And then we have two areas of application that are highly interconnected. One is multi-physics simulations, where we solve complicated and challenging problems that involve multiple physics, and that area fits into the second area, which is predictive medicine. So in the area of multi-physics simulations, we do simulations of multi-phase flows that you'll get to see today, some of them pore mechanics and fluid structure interaction, as you can see here. And in the area of predictive medicine, we develop models for mechanobiology problems, cell mechanics at the scale of a cell migration, things like that. We also develop models for prostate cancer growth. I will not get a chance to talk about any of these today. And probably the biggest area by far in my group right now is about drug delivery, where we develop models and simulation tools for delivery of multiple types of drugs, including drugs that are delivered subcutaneously or to the central nervous system, and different drug modalities, including large molecules and genetic medicines. All right, with that, I like to move to the outline of my presentation. So I will discuss different types of multi-phase flows that are interesting for us, and the phase field approach to multi-phase flow modeling. And then I'll focus on two examples. One is multi-phase flows without phase transformations. These are obviously easier because they don't involve phase transformations, which are very difficult to model. And I'll show two examples there. One is a very canonical problem where we try to solve the flow dynamics of two immiscible fluids with different properties, different density and different viscosity, for example. And that will continue with the FSI simulations that I was alluding to before. And then in the second part of the talk, I'll move to models with phase transformations. So in this case, we're looking at problems related to cavitation, boiling. And in this case, I'll focus on a single fluid rather than multiple fluids, as I was discussing before. All right, with that, I think we have a plan for the talk. So let's go ahead. I want to tell you about a few interesting problems that involve multi-phase flows, where really scientific progress is limited in my mind by absence of sufficiently strong, accurate, and fast computational methods. So you can see here on the left-hand side, this example, this is a high-speed projectile that goes through an air-water interface. And because it's a high-speed projectile, when it gets into the water, then there is also cavitation occurring. So this is a complicated problem because we have air and we have water that is being phase transformed. So from a modeling point of view, it's a complicated problem. From a simulation point of view, it's also a complicated problem. This is another example that is difficult, is an explosive type of boiling that occurs under some circumstances that is very difficult to model and simulate. And here more on the right-hand side, you see examples without phase change, where basically the difficulty of the simulation is to be able to track the topology in the fluid-fluid interface in an accurate way. And the way we usually track the topology and the fluid-fluid interface, there are multiple approaches, but two of them are explained here. The first one is when we have an explicit geometric definition of the interface. You could imagine a situation like this, where this is a fluid-fluid interface, and you have some sort of geometric description or parameterization of the fluid-fluid interface. And an example of this approach could be, for example, the front tracking method in multi-phase flows. Another approach is when you have an implicit geometric definition of the interface. So, for example, imagine this scenario where you have two droplets coming in contact, and you don't want to have a parameterization of this curve. What you want to do instead is you define a field, a scalar field, and a level set of that field implicitly defines the interface. So that is advantageous in multiple ways. One of them is that when there is a topological change in this curve, for example, then the parameterization would go singular. But this field that implicitly represents the curve, it doesn't necessarily go singular, and in fact, it won't go singular when there is a topological change in the interface. So that's advantageous from a computational point of view. And two examples of this approach are the level set approach, which is quite common, and the phase field approach. They both share this in common, but there are important differences in them, which I will not discuss in detail, but if anybody is interested, I'm very happy to talk about the differences. So with that, I like to jump into the first part, models without phase transformation. So a canonical example for this would be two nearly immiscible fluids, where each fluid has different viscosity and each fluid has a different density, but both are constant. We can, even though the density varies in space and time because the fluids move, we can still impose divergence-free constraint, have a Lagrange multiplier associated with that constraint. And that's the usual model that people use in this case. So basically, if we wanted to do the so-called sharp interface approach for this, which would require some sort of surface parameterization, then we would have to solve the Navier-Stokes equations in the red phase with these properties, the Navier-Stokes equations in the blue phase with these properties, and then we would have these these interface conditions at the interface, right? There is the velocity field is continuous, but there is a pressure jump that is proportional to the curvature of the interface and to the surface tension and the fluid-fluid interface. And that this curvature of the interface is one of the reasons why we need a parameterization of the interface to be able to compute that curvature. All right, so now one way to avoid that, if you want to avoid that, is to introduce, as I said, a scalar field that implicitly defines the interface. And you can do that using level sets, or you can do that using phase fields. The phase field model for this is the so-called Navier-Stokes-Cahn-Hilliard equation that can be derived from an energy functional. You can see, for example, excellent work by Marco ten Eikelders. And as a result of these additional field that we introduce, we don't need to track interfaces. We just need to solve one set of PDEs on a fixed mesh. Mathematically, you can prove that this diffuse interface model, the reason why it's called diffuse interface is because if this is your solution and you take a cut line through the solution, what you will see is not a completely sharp interface, but a diffuse interface that has this hyperbolic tangent functional form. And it has this parameter epsilon that indicates is related to the slope of the field. And as epsilon goes to 0, you can mathematically prove that this model converges to the model that I just showed in the previous slide. Okay. So with that, you can derive an equation that looks like this. So this is the field that implicitly defines the interface. And on the right-hand side, you have this term here, which is order epsilon. It's a small term because you want, this is the material derivative, so you want this field to be moved with the velocity. This here on the right-hand side is order epsilon, so it'll move the field with the fluid velocity up to epsilon, which is the uncertainty you have anyways in the diffuse interface. Then from this field, you recover the fluid properties, for example, density and viscosity, or only density in this case. And then you impose divergence-free constraint, and then you have a momentum balance where you can include surface tension. So one difference here with respect to level set, for example, is that when you need to define this term and when you need to recover density from the field, you need to use a specific field. In the case of phase field, that is a tan H profile. In the case of level set, that is a sign distance function. But for each of them, you need these specifics to be able to compute curvature correctly and to be able to do some of the reconstruction operations correctly. One of the key differences between level set and phase field is that in phase field, this equation moves the interface with the velocity up to epsilon, but at the same time forces the field to acquire this tan H functional form and profile that you need later in the system. In the level set approach, for example, the sign distance form of the field needs to be imposed numerically, and this creates additional computational work. So that's one way to understand this phase field model for two-component flows. This model has been applied to many different problems, so including turbulent spray atomization. This is work done in Bhaskar Ganapatha Subramanian's group a couple of years ago, where they were able to do very complex simulations of spray atomization using a special refinement technique that refines the model and the numerics at the same time. I don't have time to go into this, but it's very interesting work. I'm not going to focus on this type of turbulent spray atomization. I will focus on lower speed flows that have topology changes and contact lines and FSI later in the talk. So contact lines is, again, another thing that I think phase field models can do well. I'll show you some examples. So this example that you see here is an example of a dripping faucet. It looks relatively simple. It's relatively simple, but it's not entirely straightforward in the sense that at some point you'll see this droplet will break into two, and there is going to be a topological change. And capturing the details of that topological change, which is what we're trying to show here in these examples, is actually quite difficult from the modeling point of view, and it's also difficult, well, not incredibly difficult, but it also has some computational challenges, because exactly when the topological change occurs, inertial forces dominate, so you need a strong stabilization algorithm, even though this is a very low speed flow problem. So what we did here is we compared our simulations with experiments for this system at different flow rates. And here we're comparing the thinnest section of the thread that occurs during the topological change. We also compare the drop length with experiments for different flow rates. And we also compare the pressure at the center of the faucet. And the agreement was quite reasonable, I would say. This is another example that is interesting. Is about the stability of fluid where you are injecting a less viscous fluid into a more viscous fluid. So that's subject to Safman-Taylor instabilities and viscous fingering. So eventually the interface becomes unstable, and there is a bubble pinch-off that is not well understood. You can see here how, based on these different capillary numbers, you can think of it as a ratio between viscous forces and surface tension forces. Depending on that ratio, the interface will be more stable, as you see in the top, or more unstable, right? And one aspect that is important to be able to reproduce these experiments with simulations is a good contact line model and a good treatment of the contact line. So what you can see here is comparisons of the shape of the bubble for different capillary numbers here, different ratios of viscous forces and surface tension forces. You can see a very good agreement with experiments. What is more difficult is to capture here the point at which the capillary number, so you can think of it as the velocity. If your control parameter is the velocity that you use here for injecting air, that will lead to interface instability. This requires good numerics, good model, and a good contact line treatment. And you can see here how we got very good agreement between experiments and simulations for this contact angle and this capillary number. So that indicates that all of those things that I mentioned before, they really click and they are addressed correctly. Okay, now these problems, as I said before, they also have an FSI component to them. And we started this work a number of years ago, trying to address a very simple problem that involves multiphase fluids and solid mechanics. So the simplest problem you can think about this is you place a droplet on a substrate. And if you place a droplet on a substrate, it's going to develop an equilibrium shape in the absence of gravity. That would be a spherical cap. And it's going to develop a contact angle that is a result of the surface tensions at the three different interfaces. But what is more complicated is to understand what happens when the solid is very deformable, and it can be deformed by the droplet. So this happens when the droplet is very small, or when the material is very soft, or a combination of both, right? And what becomes more relevant there is not only the original contact angle that you see here, that is just a result of the different surface tensions, but also this quantity that is called apparent contact angle, that is with respect to the horizontal line previous to deformation, right? And you can see here that if you have different combinations of substrate stiffness versus the size of the droplet, you will get different deformations. Okay, so we started looking into this problem based on some experimental ideas that I will describe later. And the first thing that we did is we developed an FSI algorithm for this, and Yuri Basilets was involved in the development of the original algorithm. So what you have here is the fluid equations. This is conservation of mass, conservation of linear momentum, with this stress tensor that accounts for the usual viscous component plus the additional terms that come from the fluid-fluid interface and the surface tension. And then we have a standard solid mechanics model where we do elastodynamics for a hyperelastic material. And then the part that is a little bit more special in this FSI problem is the fluid-solid interface conditions that are really what determines the quantities of interest that we want to understand. So we have a kinematic compatibility constraint, that's standard. But then coming from the fluid problem, we have a static contact angle condition that can be imposed this way. And then in the usual force transmission condition that we use for FSI, we have additional contributions coming from the fluid-fluid interface. So those manifest as one normal term that is proportional to curvature, and another one that involves the surface gradient of the wettability function. So when you put this into the system, what happens is that you include additional forces here at the fluid-fluid interface that pull up the solid, for example, right? And if you look at this example before, which is the one I was showing before, you have a liquid droplet, you have vapor here or air, and then you have the substrate, and you're going to have deformation of this substrate because the Laplace pressure, that is the overpressure that is formed inside the droplet, it's pushing the solid down, and then these capillary forces are pulling the solid. Okay, so you get this type of deformation. This is an example of the displacements that you get in the solid. They are magnified, but this is displacement in X direction, displacement in Y direction. And we compare this with experiments, and we got very good agreement. So this is a zoom in of exactly this region here, which is the most challenging one. And there is good agreement with experiments. So one interesting thing that you can do with this FSI model is that, for example, there were experiments showing that if you place droplet on a substrate and the stiffness of the substrate is non-uniform, so there is, for example, this side of the solid is softer, this side of the solid is stiffer, then the droplet will move to the softer part, okay? And this was experimental evidence from this paper, and we did the simulations and we found the same result. The droplet was moving to the softer part of the solid, okay? And there is no external force being applied here or anything like that. What we wanted to know is what it would take for the droplet to move to the stiff part instead of the soft part, so that you could control the motion of the droplet or the direction of the droplet, right? And what we found is that you need very non-wetting droplets to move to a stiffer area. So if you want the droplet to move to the stiffer area, you need to make it non-wetting, but you need to make it very non-wetting. And that was the tricky part that it took us more time to understand, because if you have only a slightly non-wetting droplet, the moment it deforms the solid, it's going to sink a little bit and it's going to become wetting. So you need a highly non-wetting droplet to be able to move to the stiff part. And then we thought a little bit further about this, and we understood the mechanism that was behind this motion. And we identify a way to manipulate the system so that we could control the direction of the droplets, at least in some cases. So the result, the droplet motion occurs as a result of a balance between the Laplace pressure that happens inside the droplet and these capillary forces that pull the solid. So you cannot manipulate, given the system, given the droplet properties, given the air properties, and given the solid properties, you cannot manipulate the forces that pull the solid, but you can easily manipulate high Laplace pressure because it's going to be dominated by the mean curvature, and the mean curvature involves the curvature in two directions. So if you use two solids instead of one, you can increase the Laplace of pressure if they are very close to each other, and you can have a lower Laplace pressure if they are farther away. So by controlling the Laplace pressure, we show that we can make the droplets move in different directions. Okay. So that was one idea that we had. Another one that we explored recently was the idea of having droplets on homogeneous but anisotropic solids. The solids that we were using before, they were not homogeneous. They had a gradient in stiffness. But now we are looking into homogeneous solids but anisotropic. So one simple anisotropic model is the one that is shown here. It's the simplest anisotropic model. It's simply given by this free energy density function, where we have an isotropic part with the volumetric term and the isochoric term, and then this anisotropic component to the free energy density. That is a model proposed by Holzapfel, where we have this parameter h. This parameter h is an invariant associated with the orientation of the fibers. One way to think about this anisotropic model is a model with fibers. So the orientation of the fibers is defined by this vector d that has a particular angle given by beta. You can see it here. And then from that, you get a tensor that defines the orientation. You multiply that with c, and the trace of that is what enters the model. And then what you can see here is that this is the initial position of the droplet here at time 0. And then as time evolves, the droplet is also going to move, and it's going to move in a direction that is controlled by the wettability of the droplet and by the orientation of the fibers. And the mechanism behind this is similar to the mechanism that I described before. And you can see here how the deformation in the solid is non-symmetric, because basically the forces that are pulling the solid, in this case, they're pulling perpendicular to the fibers, so it's softer. And in this case, they're pulling parallel to the fibers, so it's going to feel stiffer. Okay. With this, what we did is we found a way to control velocity and direction of motion for droplets on anisotropic solids for a combination of static contact angles and the orientation of the fibers. And you can see here the phase diagram. So this part indicates positive droplet velocity. The droplet is moving to the right. This part indicates negative. And you can control orientation and even velocity of the droplet for picking a combination of these two parameters. Okay. All right, so with this, I want to move to the second part of the talk, where I'll be talking about multiphase flows with phase transformations. So two critical examples where phase transformations are important are cavitation and boiling. Cavitation is a very interesting problem in its own. I will not get much into it, but one example of cavitation that has been widely studied is the free collapse of a cavitation bubble. When a bubble collapses in this way, the temperature becomes very high, can be higher than 4,000 Kelvin, even higher than that, which is the temperature of the surface of the sun. And this problem itself is not very well understood. There are no good measurements of temperature. One thing that happens is that a plasma forms during the collapse, and that produces light emission. And this is exactly the problem we're working on right now, how the plasma is generated, but I will not be talking about that. But what happens is that this collapse problem, even though it's highly complicated, is actually much better understood than the inception of bubbles. How these bubbles are created rather than how they collapse is much more difficult to understand. Cavitation also has applications in science and medicine. So one relatively recent work that we did with this was studying the collapse of cavitation bubbles, not in a free fluid, as you can see here, also not in a free fluid that is adjacent to a solid wall, which is another canonical example, but in a soft porous material. And this is important for drug delivery and traumatic brain injury. And what we did here was we came up with an extension of the so-called Rayleigh-Plessé equation, which is a very simple model for cavitation. And we accounted for the effect of the porous material transforming that equation in an integral differential equation that can be solved with simple numerical methods. And we were able to show that that equation matches the results of a poroelastic simulation. Okay. The other example that is very important, of course, is boiling for electronics cooling and many other different applications. All right, so then I'll be focusing on cavitation for now. So the challenge with cavitation, or one of the challenges, is that we need to model phase transformations. So what you can see here is a standard model for cavitation that has been widely used for cavitation in naval application, and it's a very good model. But we want to address a challenge with this model, which I will walk you through now. This is conservation of mass, conservation of linear momentum. And then we have this additional equation that represents phase transformations, and it has these source and sink terms on the right-hand side that determine how much of the liquid is transforming into vapor or how much of the vapor is transforming into liquid. And if you look at these functions, I think you can see right away that there is a certain phenomenological component in them, and there are these two parameters in particular that are difficult to calibrate. They may depend on the flow conditions and on Reynolds number. So there are no universal parameters that would apply to all flow conditions. And another thing that is important is when you want to understand exactly the physics of cavitation inception, how these bubbles are formed at the beginning, basically here you're going to be guided, your understanding will be guided by these model equations, which we don't know exactly how accurate they are in those conditions. So that's the modeling challenge we wanted to address. So to do that, we went back to a theory for phase transformations that was actually proposed by van der Waals. And the idea is all based on this free energy. The free energy that you normally use for fluid mechanics would be one that depends on density and temperature. And if you ignore the red terms for now, you would have a free energy function that depends on density and temperature that looks like this. This determines all thermodynamic relationships in the equations, including the volumetric and thermal equation of state. And if you check any thermodynamics book, the first thing you read is that this function needs to be convex, okay? So van der Waals' idea was this function doesn't need to be convex if you add this additional term that accounts for the interfacial energy. The fact that this function needs to be convex is a limitation of the free energy because it's ignoring interfacial effects. That was van der Waals' great idea. And that allows you to use non-convex functions here that open possibility to use all of the state-of-the-art tools for phase transformations. So what happens here is that if you want to develop a model like this, you need this function that now can be non-convex. All of its parameters can be obtained from thermodynamic data, equilibrium thermodynamic data. This additional parameter can be obtained from surface tension. And what you can show, even mathematically in some cases, is that when you look at this function and you look at convexity of this function in a functional sense, you can actually show that the function is convex in functional sense, even though if this function is not. And that gives rise to solutions for the density field that varies smoothly between the vapor and the liquid. Okay, so this is really a non-equilibrium thermodynamic theory of phase transformations. It doesn't rely on the mass transfer functions that I mentioned before. All right, so the governing equations that follow from this free energy are the so-called Navier-Stokes-Cahn equations. The only thing you need to do at that point, once you have the free energy, is to use the Coleman-Knoll approach. So-called Coleman-Knoll approach is a classical technique in continuum mechanics that, given a free energy, will tell you exactly how does your stress tensor and your heat flux need to look like for the model to be compatible with the second law of thermodynamics. Okay, so this is what was done here. So given the free energy, you use the free energy and the balance laws, and from the Coleman-Knoll approach, you get the stress tensor and you get the heat flux. Okay, the heat flux turns out to be the same as we normally use for Fourier, or at least a compatible heat flux. And then for the stress, you get the normal viscous stress, and you get this additional stress that emerges from the interfacial terms, okay? And the interesting thing about this model is that it has been around for a pretty long time, 40 years now, but there were basically no meaningful computations until very recently. And at the time when I first knew this, I thought there must be a reason for that. But to be honest, I never thought it was going to be so difficult to solve these equations. And I'm not saying we can solve them now, but we can do much better. And we came up with this approach to solve these equations that we call direct van der Waals simulation, because the only thing you use in the modeling approach is the van der Waals idea. And with this approach, the computability can be extended from micrometer to meter scale. And it enables computations of high speed and well-bounded flows that were not really possible before. And the reason for this, I try to explain here. So this approach, direct van der Waals simulation, overcomes three critical challenges. There is still a lot of room for improvement for this, but at least with what we have done, we can compute some cases. So the first challenge is that the isentropic solutions to these equations, they're not hyperbolic waves, they are dispersive waves. And most algorithms for compressible flow, they make use of the hyperbolic eigenstructure of the equations. And when you don't have that hyperbolic eigenstructure, it's unclear what to do. Challenge number two refers to this limitation. Without any specific treatment, computations beyond micron scale are unaffordable. And there was previous work addressing this challenge. This challenge we didn't really solve ourselves. And the reason for this is that there is one parameter that controls two things at the same time. And you cannot, if you don't do any special treatment, you cannot satisfy the two requirements that you need, which is you need to be able to resolve the interface, and you need to be able to control the surface tension to make it match what the values that you want. And challenge number three is that when you have a liquid vapor mixture, the speed of sound can become very, very small. It can be of the orders of a few meters per second. So basically, in a problem like this, you can get shocks very easily. You can get, even in a relatively low speed flow, you can get almost hypersonic flow. And these shocks, they don't have the usual structure that we are used to. They have a different structure, in some case, that is that of a dispersive shock, which is much more complicated. So I'll just give a very quick overview of challenge one and challenge two in the time that I have left, which is only 4 minutes. So challenge one, it's an interesting one. So as I said, compressible CFD is dominated by the idea of upwind discretizations based on the direction of hyperbolic waves. That includes the fluid velocity, speed of sound, etc. But what we found out is that if we just use that idea, then what's going to happen is that in some parts of the domain, and that part of the domain is usually the liquid vapor interface, in addition to these hyperbolic waves, we'll have a strong dispersive wave that can move exactly in the opposite direction to the usual hyperbolic wave. So if you keep using the upwind from the hyperbolic wave, you basically have a downwind simulation, a downwind algorithm that is very unstable, and it will blow up immediately, okay? So these dispersive waves, they have been seen in experiments of multiphase flows, and they're much more complicated than hyperbolic waves. They cannot be easily identified and associated with a velocity. You cannot diagonalize a system the way you do it in hyperbolic waves. So basically, it took a lot of different attempts to really understand what's going on with the waves. This is why we call this paper Q-various wave, because it's difficult to understand how the waves are moving. And we have by no means perfect solution to this, but it really changed dramatically when we understood this, our ability to compute. Challenge number 3 is related to what I mentioned before. The structure of the shocks is different for these equations. There are dispersive shocks. And what we normally use for shocks is in finite elements is a discontinuity capturing operator. And we have shown that the classical discontinuity capturing operators, they can act as entropy sinks for this equation. So if we use blindly a classical discontinuity capturing operator from gas dynamics, we have shown that they can be entropy sinks. So they are doing exactly the opposite of what you want them to do. So a new discontinuity capturing operator needs to be designed for this. And again, we have by no means a perfect solution to this, but we did come up with something that we published in JCP recently. And this was work that involved also Guglielmo Scovacci and Tom Hughes, where we came up with a new discontinuity capturing approach based on the ideas of phase field. And you can see here some examples. So this is the reference solution for a 1D shock problem. The proposed approach is the phase field DC that you can see here in orange. You can also see here in orange. And it's compared with a classical discontinuity capturing with no scale. So this would be an absolutely standard discontinuity capturing from gas dynamics. This one here is our first approach to DC, which was based on the very simple idea that normally when you have gas dynamics, you want to use DC, but when you have incompressible flow or nearly incompressible flow, you don't want to use DC. And in these problems, you have the two at the same time in the same problem occurring, because you have a mixture of liquid that is nearly incompressible and you have vapor that is very compressible. So this first idea, which was helpful, but certainly not a very good solution, was the idea of reducing dramatically the intensity of the DC in the nearly incompressible region, the scale DC. And this was an idea that involved already a reformulation of the DC to avoid the entropy sink that I was mentioning before. And you can see that it really does a better job. Okay. All right, so then we put all of these ingredients together and we did some simulations. I will not go through the details of them, but this is one example where we solve flow past a hemisphere, and we compare our simulations with experiments. And the good thing, as I said before, is that there are no tuning parameters in this model. Even if I wanted to fit parameters to match the results, I cannot do that because I don't have enough free parameters to do that. And the results are pretty good, I would say. So with that, I think I'm ready to conclude. My time is also up, so I'm very happy to take any questions if there are.
Great, great. Thank you, Hector, for the great presentation. Now we open the floor for questions. So if you have any questions, please directly unmute yourself and and ask. Oh yeah, so there is a question from Shashwat. So Hector, maybe I will read the question to you. So thank you for taking the time to explain the intricate mathematics behind your work. I was more curious about the computational aspect of it, since you employ IGA elements and considering multiple coupled physics. I was curious as to how well you are able to scale your work in parallel systems, and what do you see as the current challenges in that aspect?
Yeah, thank you for the question. So I don't see a huge limitation in scalability. Some of not the cases that I presented here, but some other cases related to cavitation in channel flow, we run them in over 2,000 compute cores. These are CPU computations. And the scaling was pretty good. So we have very good scaling up to 2,000 processors. So I don't see huge limitation in scalability. What I think it would be interesting and potentially impactful is to be able to design algorithms that can really exploit GPU architectures for this work, which is not particularly easy.
Yes. Thanks, Hector. Okay, great. Thank you, Shashwat. Any other questions?
Hi, can okay. Hi, Professor. Can you hear me?
Yes, yes.
Yes,
Okay, so
yes.
first, thank you, Dr. Hector, for this impressive presentation. So I'm very interested in one problem you have mentioned in the slides. I call it as the droplet deformed solid problem. Like the droplet is moving in a plate, like the plate is from the stiff to like gradually changing from stiffness, right? So I think this problem is a little bit anti-intuition to me. Like, what kind of solid can be like deformed by a droplet of fluid? So I mean, I want to like have more on understanding on the description for the problem statement.
Yeah. I'm trying to go back in my slides, but they seem to be. Oh, okay. Now I can go back. Yeah. That's a good question. So let me try to give an answer to that. Okay, so whether the droplet can deform the solid or not depends on the ratio of these two quantities. One quantity is r, the radius of the droplet. The other one is the surface tension at the fluid-fluid interface and the Young's modulus. You need R to be smaller, significantly smaller than this ratio. What does it take for you to be able to do that? So you need a very, very small droplet, or you need a very, very soft material. And I'll give you an example. If you want to see significant deformation of a solid for a droplet, one example that was shown in the literature where they have these experimental results, the solids they were using, they were very soft gels. The Young's modulus was in the order of 5 kilopascals, something like that. And the droplet size was in the order of 100 microns. So that's what it takes. For example, 5 kilopascals Young's modulus, 100 microns droplet, or you could do 50 kilopascal, but then the droplet needs to be, instead of 100 microns, 10 microns, right?
Okay, I see, I see. It's a very interesting problem.
Yeah, thank you.
And another follow-up question is like for this problem, what kind of method you use for the like the solid and the liquid interaction part?
Yeah, let me go back to to my slides. So this is the equations that we solve. Was your question more about equations or about
Yeah. It's more about equation. Yes.
equations? Okay, so this is a Cahn-Hilliard Navier-Stokes model. So it's a model for two immiscible fluids with different properties, different density, different viscosity. And this is the solid model. It's elastodynamics for a hyperelastic material. So this is a very standard model. This is a phase field model of two component flows. You don't have to use phase field. You could use something else. But the point in which phase field becomes helpful is when you want to impose these interface conditions. So contact angle it becomes relatively simple to impose, and this force transmission condition also becomes relatively simple because all of these quantities that you have here, one is the curvature of the interface that you can compute from your mesh. This one is just a function of the density, and this is just the surface gradient of a function that depends on density. So all of this is easily computable. One thing that is interesting about this problem also is that, and this is a little bit of a problematic thing, that is, if you take the limit to the sharp interface, then you'll have point forces on the solid. And that, depending on the dimensionality of the solid, may render an ill-posed problem or a singular problem, and that's well known. So the way phase field treats that is by regularization. You expand the force in a consistent way over a finite region. So this would be my quick explanation of the modeling technique. Does that help in any way?
Yeah. I think this the equation makes sense to me. And so in in this slides in the figure B, right? If I understand correctly, does it involve some kind of mesh deformation stuff?
Yes. So the fluid problem occurs on a moving domain. So as the solid deforms, the solid, it's mapped into a reference configuration, but when you map it to the current configuration, it's obviously moving, right? Like any solid mechanics problem. And the fluid domain changes as a result of that. And then in order for us to be able to solve a fluid problem on a moving domain, the first thing we do is, and again, there are other ways to do this, right? But the first thing we do is we take these equations, we write them in ALE form, and then using the displacement values that come from the solid, we move in a consistent way using an elasticity auxiliary mesh motion problem, the entire fluid domain, and then use that information into the ALE form of these equations. So it's a standard, the FSI is a standard body-fitted algorithm based on arbitrary Lagrangian Eulerian formulation for the fluid and Lagrangian formulation for the solid.
I see. Thank you for your explanation. And I also have a final follow-up question related to this problem because this problem is really interesting to me. Like the problem is like more about like how are you able to find like this kind of new and interesting problem for the simulation?
Well, that's an interesting question. I don't know if I have a system for that, but reading the literature, I would guess would be the talking to people. Talking to people is the best part of research, right? So you do not only get to meet people, but you also get to learn about new problems. So talking to people, I think, is the best advice.
Sure. Thank you, Professor, for your time and answer.
Sure.
Thank you. I heard there was another question. Could you speak? Hello.
Hello. Hello. Thank you for your great presentation. I have a question about that last phase transformation problem. So it is actually solving the compressible Navier-Stokes, right? Then doesn't it have a time step size restriction a lot? Is it not that harsh restriction? So it is feasible to do the simulations efficiently?
Yeah. So it's let's look into the equations quickly. So it's in fact, as you said, compressible Navier-Stokes, but there is something that is important to mention here, which is this is a general compressible model, but in the gas phase, it's very compressible, but there is also the liquid phase, and they are defined by the same density field. It's a continuous density field. But in some parts of the domain, you have extreme compressibility, and in some parts of the domain, you have nearly incompressibility. So that's very challenging from the numerical point of view. And you need, like, time stepping usually is different for compressible and incompressible, right? But here you need a unified time stepping. And the other thing that is important about time stepping is that if you look at this part of the stress tensor, this is a third derivative in space. So if you were to use, for example, explicit algorithm, your stable delta t would scale with delta x cubed. This is also why I mentioned that it would be interesting to think about ways to implement this efficiently in GPUs, because the approach that would make it very efficient in GPUs, all of us immediately, would be explicit, right? But explicit would have that dramatic constraint on the time step. So time stepping is very important.
So one more follow-up question is, so is this done with IGA, with hex meshes?
So yes. So in this was done, all of it was done with hex meshes. In some cases, we used C1 continuity. In some other cases, we use C0 continuity only, but it was all done with hex meshes and IGA.
Then just one more question is then, does this weak form can be written as a sum factorizations easily? And also, does it have a Hessians a lot in the weak form evaluations?
Sorry, I didn't understand the question. If the weak form can be written
so this weak form, is it good structured to be sum factorized and can be efficiently evaluated? And if so, then does it have a lot of Hessians to be evaluated at this weak forms? Oh, okay.
Right. So there are multiple ways to write the strong form and the weak form. To answer your question precisely, I think there is at least one way in which only one Hessian is involved, which is not the conservative form that you're seeing here. It's a non-conservative version of the equations. But yeah, even if you have a Hessian in your weak form, if you use IGA with C1 continuous elements, you don't really need to worry about anything, right? That Hessian can be computed, and the integrals will be well defined. If you want to use C0 elements, then you normally introduce additional variables in your finite element space. For example, one that represents the Hessian, and you carry that as an additional variable. And then at that point, you can use standard C0 elements.
Hector, which variables do you use? Pressure primitive, density primitive, conservative, some other?
Well, we have tried many different variables. Actually, we built a code that automatically writes the entire finite element code for an arbitrary set of variables. We have used entropy variables. And what we are using the most is a combination that includes velocity, temperature, and the log of density.
Log of density.
Yeah,
okay.
Because that prevents negativity of the density. And it's still relatively easy to compute it. In our experience, for the cases we've done, it performs similar to entropy variables.
Have you tried pressure primitive? So pressure, velocity, temperature. It tends to respond better for nearly incompressible.
Yeah, the issue.
But then your free energy is kind of,
Right.
I'm more used to ideal gases and explosives where that doesn't work, but just
the issue with pressure is you cannot get the density back from it.
Got it. Yeah, same as with
Yeah.
Got
it. Great. Thank you, Hector, Joming, and Yuri, for the discussion. Are there any more questions? Okay, if not, since it's already an hour, let's thank Hector again for the presentation.